proper description of multi-component diffusion in metals, glasses, steels, and alloys is important in a wide variety of processes such as bonding, cladding, controlled heat treatments, and surface modification. The diffusion couple technique is a powerful experimental method that allows the determination of interdiffusion coefficients in alloys, metals, and glasses. As an example of a diffusion couple, I show here on the left a ternary mixture of three components: potassium oxide, strontium oxide, and silicon dioxide, that is relevant for diffusion in glasses. The left compartment and the right compartments are of different compositions. The three components are allowed to interdiffuse at a temperature of 1071 Kelvin, and the composition profiles at the end of a specified time period, in this case 4.55 hours, are determined experimentally and plotted here. The green squares are for potassium oxide, and the red spheres are for strontium oxide. This is the weight percent on the y-axis, and the metano plane is shown by the dashed line. So this is the left compartment, this is the right compartment equilibration. We note that strontium oxide experiences an undershoot in the left compartment and an overshoot in the right compartment as it equilibrates. Diffusion coupling effects are strong, and the interfacial diffusion fluxes are described by a square matrix of diffusion coefficients D11, D12, D21, and D22. This is the gradients in the mass fractions of components 1 and 2. There are only two independent fluxes because the mass fractions add to unity. The experimentally determined composition profiles may be used to determine the Fick matrix of diffusivities, and the values for this set of experiments are determined to be given as shown here. Particularly noteworthy is that the coefficient D21 by component 2 is strontium oxide, component 1 is potassium oxide. D21 is larger in magnitude than D22, the diagonal element, and is of opposite sign. Therefore, component 2 experiences a strong influence from the driving force for component 1, because it's strongly coupled, and such strong coupling results in undershoots and overshoots. When plotted, the compositions are plotted in composition space. Here on the left, the bottom axis, we have the weight percent K2O, and on the y-axis we have weight percent strontium oxide. The equilibration trajectories in the left compartment, this is time t0, that's the initial composition. This is the initial composition in the right compartment, and they equilibrate following a serpentine trajectory. This composition is at time infinity, as it were, in this case 4.55 hours. And the serpentine equilibration trajectory is a characteristic of uphill diffusion. In today's talk, I ask the question, what determines the serpentine character when the experimental data are plotted in composition space, as is done here? The modeling details are provided in my two papers. First one published in Chemical Society Reviews 2015, and the second one published in Chemical Engineering Science in 2019. Watch also my video Uphill Diffusion on my YouTube channel. Let's now examine the anatomy of the serpentine trajectory in more detail. In order to understand the anatomy of the serpentine equilibration trajectory, we examine the values of the thick diffusivity matrix in greater detail. We determine first the two eigenvalues, lambda 1 and lambda 2. Lambda 1 is 1.33 times 10 minus 13 square meters per second. Lambda 2 is significantly smaller in magnitude and has a value of 3.21 times 10 minus 17 square meters per second. Corresponding to each of these eigenvalues, we determine the eigenvectors. Corresponding to lambda 1, we have the fast eigenvector with elements shown here, and corresponding to lambda 2, we have the slow eigenvector. We construct a modal matrix with the two eigenvectors E1 and E2 placed side by side that yields a square matrix with 4 elements shown here. And an important property of this modal matrix is that if we pre-multiply the thick diffusivity matrix by the inverse of the modal matrix and post-multiply by the modal matrix P, we have a square matrix that is diagonal, and the diagonal elements are the eigenvalues. So this is the matrix diagonalization procedure. The details of the matrix diagonalization procedure and how that impacts on multi-component diffusion characteristics is described in this textbook I co-authored and published by John Wiley in 1993. Details of the calculations for the ternary glasses is obtained from my paper from Chemical Engineering Science 2019. So we look at the experimental data on the equilibration trajectory in composition space and plot the eigenvectors here. These are the red lines. This is the fast eigenvector. The blue line is the slow eigenvector. So this is the initial composition in the left compartment, and this is the initial composition in the right compartment. The initial trajectory is strongly influenced by the fast eigenvector in both compartments. As equilibration proceeds, the trajectories are then determined by the slow eigenvector as the system approaches equilibrium. So the experiments show that the component mass fractions or mass percentages shift allegiance from following the fast eigenvectors initially to then follow the trajectory dictated by the slow eigenvector as equilibrium is approached. Put another way, the fast eigenvectors and the slow eigenvectors provide the bounding trajectories within which the experiments must lie. It is also possible to determine the eigenvalues and lambda 1 and lambda 2 by examining the serpentine trajectories in composition space. Details of such calculations are provided in my textbook from 1993. See also my paper in chemical engineering science.